Hi guys, my name is Samuel Jasper from CSC department, currently in my first year. My topic for Tech Talk in applied physics is dynamic single mode lasers. What are single mode lasers? Single mode lasers are lasers that emit single mode lasers are lasers that emit light in a single spatial mode, which means that the light travels in a well-defined narrow beam with a specific direction. This type of laser produces a coherent beam of light with a uniform wavefront, typical in the form of single transverse electromagnetic TEM mode. Unlike multimode lasers, which emit light in a multiple spatial modes, single mode lasers generate a cleaner and more focused beam of light with a minimal divergence. How single mode lasers work? Laser cavity design. A single mode laser typically has a resonator or cavity that supports only a single longitudinal and transverse mode of light. The size of the cavity is usually small compared to the wavelength of light, ensuring that only a single mode, the fundamental mode, fits within cavity. Gain medium. The laser uses a gain medium, example semiconductors or a gas that amplifies the light. The gain medium is excited by an external energy source, and as the light is reflected back and forth between the mirrors of the cavity, it becomes coherent and amplified. One of the mirrors in the cavity is partially transparent, allowing a portion of the coherent light to exit the laser as the output beam. This beam is typically collimated and has a high degree of coherence. Differences between single mode and multi-mode lasers. Beam quality. Single mode lasers produces narrow and focused beam and with high spatial coherence, whereas multi-mode lasers emit a broader beam with low spatial coherence. Beam divergence. Single mode laser have minimal divergence over long distances while multiple lasers exhibit more divergence when compared to single mode lasers. Complexity. Single mode lasers are typically more complex to design and manufacture due to precision required in the cavity designed to support only one mode. Why are dynamic single mode lasers important? Dynamic single mode lasers are important because they combine the advantages of single mode lasers with the ability to adapt the varying conditions and requirements in real time. These layers are capable of adjusting the operating parameters dynamically, such as the wavelength, intensity, or beam characteristics, making them highly versatile for advanced applications in research, communications, and technology development. Here's why dynamic single mode lasers are important. Wavelength tunability, precise control of wavelength. Dynamic single mode lasers can be tuned across range of wavelengths, allowing user to adjust emission of specific needs. This tunability is crucial in applications such as spectroscopy, wavelength division multiplexing communication, and laser spectroscopy. Whereas the ability to choose a precise wavelength can enhance sensitivity, resolution, and efficiency. A tunable single mode laser can be used in a wide range of fields from biomedical imaging to medical analysis to chemical analysis, where different wavelengths are required for various types of interaction with materials. Flexibility in communication, optical networks. In fiber optic communications, dynamic single mode lasers are used in wavelength division multiplexing, where different signals are transmitted simultaneously over the same fiber at different wavelengths. Being able to dynamically adjust the wavelength allows for more efficient and significant bandwidth management and improved signal transmission. These layers can be dynamically adjusted in response to changing network conditions such as power fluctuations to maintain optimal performance and reliability in optical communication systems. Enhance beam quality and control. Dynamic single mode lasers often used in high performance applications like LiDAR or optical trapping offer enhanced beam quality and reduced noise compared to multimode lasers. This enables more accurate measurement and better resolution. Dynamic lasers can also adapt the shape of the output beam, improving the precision and focus of the light, which is crucial in applications like laser cutting, microsurgery, and 3D printing. Laser characteristics. Laser characteristics refers to fundamental properties of laser, and the laser stands for light amplification by stimulated emission of radiation that define its performance, functionality, and potential application. These characteristics include the laser coherence, beam quality, wavelength, power, and other factors that make lasers suitable for a wide range of applications, from communications to medical treatments and to chemical analysis. Emission of single wavelength and spatial mode. The emission of Single wavelength and spatial mode is a key characteristic of single mode laser. This refers to laser's ability to emit light with a very specific wavelength, chromatic light, and a single spatial mode, meaning the less beam is emitted in a well-defined and a focused direction with minimal spread. This characteristic is crucial for many precision applications as it ensures the laser produces a clean, narrow beam that can easily control and manipulate. Let's divide this into two segments. Number one, emission of a single wavelength, monochromatic light. Definition. A single wavelength means that the laser emits light with a very narrow range of wavelengths. Typically, a single wavelength often referred as a monochromatic light. In this case, the light has a very specific frequency that is consistent over time. The laser gain medium is stimulated to release photons through the process of stimulated emission, and the optical cavity is designed to support only a specific wavelength, thus filtering out other wavelengths. Importance. The emission of a single wavelength ensures that the light produced is highly coherent, meaning the light waves are in the phase both spatially and temporally. This makes the laser beam more predictable and effective for applications that require precision wavelength control, such as spectroscopy, communication, and infometry. Example: a helium and neon laser, that is HENE laser, typically emits a red light with a wavelength of 632.8 nanometers, providing a clean and stable monochromatic light. Emission of a single spatial mode. Spatial mode refers to the spatial distribution of the laser beam electromagnetic field. In a single mode laser, the light is emitted in a well-defined beam with a single transverse electromagnetic mode, meaning the laser spatial field distribution is uniform and focused. How it works, the importance of laser cavity or the resonator plays a key role in ensuring the laser operates in a single spatial mode. The cavity is typically small relative to the wavelength of light, allowing only the fundamental transverse mode to propagate. This results in a laser beam with a minimal divergence, meaning it stays narrow over long distances. Importance. Emitting light in a single spatial mode ensures that the beam is well defined and well collimated, focused, and coherent, making it ideal for precise applications such as optical communication, microsurgery, and high resolution imaging. A single mode laser typically has better beam quality compared to a multi-mode laser, which would emit light in multiple spatial modes and result in less focused and more divergent beam. Working principle of dynamic single mode laser. Single mode laser setup. It's all starts with the basic setup of single mode laser with a gain medium and optical cavity. The laser emits monochromatic light in a single spatial mode after the gain medium is pumped, leading to stimulated emission. The dynamic single mode laser incorporates mechanism to dynamically control wavelength tuning, intensity control, mode control, temporal properties. Feedback mechanism. The laser output is continually monitored with real-time adjustments made to maintain optimal performance such as wavelength, intensity, power, and etc. Finally, the tuned laser output is achieved with a real-time adjustment applied based on the feedback. Applications of dynamic single mode. Telecommunications and optical networks. Wavelength division, multiplexing, WDM. In optical communication systems, dynamic single mode laser can tune their wavelength to allow multiple signals to be transmitted over a single fiber. This increases the bandwidth and capacity of optical networks, making them more efficient. Dense wavelength division multiplexing WDM. These layers are used in high capacity communication systems where the wavelength of the laser can be dynamically adjusted to maximize the use of available optical fibers. Spectroscopy. Raman spectroscopy. Dynamic single mode lasers are used to provide a precisely tuned wavelength for Raman scattering experiments where the wavelength of the incident light needs to match specific or molecular vibration. In absorption spectrometry, where the absorption of light by molecules is measured, lasers with tunable wavelengths are essential to probe with different molecular species. This technique uses a dynamic single-mode lasers to create a plasma on the surface of a sample for elemental analysis. The laser wavelength and intensity are dynamically adjusted to optimize the plasma formation. Quantum technologies. Quantum key distribution in quantum cryptography, dynamic single mode lasers are used to generate entangled photons for secure communication. The wavelength and the intensity of the laser are dynamically controlled to meet the requirements of quantum protocol. Dynamic single mode lasers are used in quantum sensors to measure small changes in physical quantities like temperature, pressure, or magnetic fields with extremely high precision. Quantum computing lasers with precise control over wavelength and pulse duration are used in quantum computing systems for manipulating qubits in optical quantum computers. Medical applications, laser surgery. In ophthalmology, dentistry, and vascular surgery, dynamic single mode lasers are used to adjust power and wavelength for precise cutting or tissue removal with minimal collateral damage to surrounding tissue. Optical coherence tomography (OCT) is an imaging technique used in medical diagnostics to capture high-resolution images of tissues. Dynamic single-mode lasers are used to control the wavelength and intensity of the light to achieve optimal imaging resolution. Endoscopy. Dynamic single-mode lasers are used in minimally invasive surgical procedures and diagnostic imaging, where wavelength and intensity control is needed for precise tissue interaction. Technology is enabling dynamic behavior, crafting tuned lasers. In this type of laser, diffraction gratings inside the laser cavity or in the external cavity can be used to selectively reflect and filter different wavelengths by adjusting the angle of the grating. The effective wavelength of the laser can be tuned. This allows the laser to dynamically switch between different wavelengths or finally adjust its wavelength within a specific range. Applications: it is used in fiber optic communication, lidar systems, and scientific instruments. Acousto-optic tunable fiber filters. Acousto-optical modulation and filters use sound waves to modulate the light passing through a crystal. The frequency of the light wave can dynamically control the wavelength of the transmitted light. By adjusting the frequency of the acoustic waves, the laser can dynamically tune its wavelength. This technology is capable of extremely fast tuning and can be used in a variety of applications where rapid, precise adjustments are needed. Application: it is used in spectroscopy, imaging system, and optical communications. Temperature control. Temperature control is one of the simplest and most common methods of tuning the wavelength of semiconductor laser. The wavelength of semiconductor laser is temperature dependent, meaning the refractive index of the material changes with temperature. By cooling or heating the laser diode using a thermoelectric cooler, the emission wavelength can be tuned over a narrow range. Application: it is commonly used in tunable diode laser for applications in spectroscopy, environmental monitoring, and telecommunication. Advantages of dynamic single mode laser. Wavelength tunability. One of the most significant advantages of dynamic single mode laser is their ability to precisely tune the emission wavelength in real time. This enables applications that require fine wavelength adjustments such as spectroscopy, optical communications, and material processing. High power and efficiency. High power output in a single mode. By using a single mode, these lasers concentrate the energy in a narrow beam, resulting in higher intensity for a given output power. This is particularly useful in applications like laser cutting, welding, and medical surgeries, where high power is needed in a small area. Where the high power in a small area is required. Challenges and limitation. Complexity of design and control. Achieving dynamic behavior in a single mode laser often requires complex and sophisticated control systems such as external cavity tuning, electro-optic modulators, and feedback loops. These systems require precise calibration and real-time adjustments, which can increase both design complexity and system cost. Cost and manufacturing complexity. The advanced components and precision required for dynamic single mode lasers make them expensive to manufacture. Technologies such as external cavity designs, modulators, and temperature control systems add to the cost, which can limit their widespread use in the low budget application. Manufacturing complexity. The need for high precision fabrication and assembly of the laser components can lead to challenges in scaling production and ensuring consistent quality across units. Conclusion: Dynamic single mode lasers are powerful and versatile tools that offer high precision wavelength tunability and narrow spectral alignments, making them indispensable for applications requiring high resolution, stability, and flexibility. Their ability to produce stable narrow beam output with minimal noise makes them ideal for demanding fields like telecommunication, medical diagnostic, material processing, optical sensing, and quantum technologies. Key advantages include the ability to precisely control the emission wavelength, generate high quality focused beam, and adapt in real time to changing environmental conditions. This enables a dynamic signal mode laser to excel in areas that demand fine-tuned performance such as spectroscopy, imaging, and high precision metrology. Thank you for watching.